Hi, and welcome to Engineering 255. Today we're going to talk about Chapter 9. We have two videos to explain the content of the Chapter 9, which is about the center of the gravity and the centroid. This is a very important idea. It involves some of the geometry and also some of the calculus. You have to do some integration to find out the definition of the central of the gravity and also the centroid. We're going to start with this video, which is going to explain the concept of the center of the gravity, center of the mass, and also the centroid of a body. So it's going to be like 3 dimension instead of just 2 dimension. Let's look at the purpose of this chapter. So in this video, we are going to explain the concept of these 3 different things: center of the gravity, center of the mass, and the centroid. We also going to show you the method to determine those location. If you have an arbitrary body, how do you find out the location of these 3 things? Now, just want to give you a heads up, what is the difference of these 3? So if you look at this table, it kind of summarizes the important thing about these 3 different ideas. The center of the mass we can simplify as the cm, and this is the point where an object have the total mass is considered to be concentrated. It sounds very simple. You just kind of sum all the masses into a single point, and that is what we call the center of the mass. Similarly, if you look at the gravity, and you should know the difference between the mass and the gravity, the center of the gravity is it's kind of similar to the center of the weight. You think about not just the mass, but as the weight. If you sum all the weights together into a single particle to represent the body, and that point is our center of the gravity or the center of the weight. The centroid is not based on the mass, or is not based on the weight. It's based on the geometric center. So you're looking at the shape of that. Let's say you have maybe like a trapezoidal shape. If you look at the y direction, the trapezoidal y direction, and you probably will say, well, this is the trapezoidal direction shape. You look at this direction and you will say, well, this is going to be the middle of the y direction. And you look at the x direction, it looks like this is going to be in the x direction as well. This is true because the shape of that just simply tells us we can just find a midpoint. It's going to be the centroid of the object. However, if I told you, well, the object has a different amount of the mass, if we have a more heavier component here, where the rest of the component is lighter, then the central of the mass or the center of the weight is going to be different from the centroid. So this is like a basic difference between these 3 different concepts. Now on the third column that we showing here, just wanted to tell you, if you look at the center of the mass, obviously it's not going to be depends on the gravity. So this is kind of a physics that you read when you study the physics. The mass is not going to change if you go to different planet, right? Because the mass doesn't really depend on the gravitational force, but the center of the wave might depend on the gravitational field. So it's a simple definition, and we hope that you have a basic idea what we are talking about, and we're going to study more about this. So why do we care? Right, so here we show you one of the application when we are study the structure. Remember the previous chapter, we're looking at the structure, arbitrary shape of the being or the machine or the friend. we always have to consider about the weight, even though in the trust we ignore the weight. However, in realistic, when you design those kind of things, you do need to consider about the weight, especially when the weight is huge. Um, for the uniform shape of the object, we don't really care about this idea about the center of the mass or the center of the weight because it's a uniform. However, if the object is not uniform, like this water tower, for example, and you have a stair on one side and the other side you don't, and at the bottom of this tower you have additional structure, looks like a bridge so you can reach to the bottom of this water tank to do some maintenance or do some open valve or closed valve, that kind of thing. So it's a really complicated shape. How do we find the weight and its location? To find a weight probably is simple. You just kind of sum all the weight together and then you can get the resultant. But the location, where the location of this whole structure is always going to be at the center of the cylinder here, it's not necessary, because think about this part of the bridge. It's going to change its position of the center of the weight. So why does it matter? Because if the total weight is not right at the center, you have to shift it to the other side. Then when you calculate the support, we use the entire structure to calculate the support. The reaction force will be different. If this one is all uniform, then each one of this leg is going to support the same amount of the force. If one side is heavier, like this side is heavier, you are expecting this leg here is going to support more of the load. So we need to know how to find the center of the mass or the center of the weight, and so that we can do a precise calculation. The other example we can show you is that if you drive car, a lot of people like the SUV car right now because it has a lot of function, not only just because the car is larger, but it's kind of convenient to have a larger space. However, one weakness of this kind of a vehicle is that it's very easy to tilt over. And the reason for that is that you think about this is a higher uh, car, right? The higher car meaning your center of the mass will be at a higher location. If the center of the mass is the higher location, and then you give any of the force that from the side, it's very easy to make it tip over. To make it safer, not so easy to uh, tip over, is that you have to make the bottom to be heavier so you can lower the center of the mass. By lower that, it will be harder for this one to tip over. Okay, you can. That's a very simple idea. If they say if you have an object look like this as opposed to an object like this, right? This one here you have a heavier bottom, so it's not easy to make it turn unless you have a really hard force to hit this. Otherwise, it's not going to turn. But this one here is, it looks like itself it will be tip over, turn to any of the direction. If you give any of the force, it will be very easy to turn. So make the center of the mass lower will make your object more stable, and that is purpose that we wanted to study this subject. All right, so now let's look at a basic idea. So over here you see an arbitrary shape, and this is a body. This is a three-dimensional body. And we can separate this whole body into smaller pieces. For example, this is just a small piece right here. We can say, oh, this small piece has certain amount of the weight. So the weight is the dW. D just simply represent this is a sample of the body, and we just get a very small particle of the weight. The weight is going downwards because it's in the z direction. Then each one of them has similar things like a small body and the weight is going downwards, everything is going to go to the same direction. Our purpose is that can we find a location where we can sum all these weight together and we represent the total weight to be W. So this W simply represents all the small w together. But this part is simple, right? You just sum all them together. The hardest part is where's the location? Where's the location if I just want to represent everything into a single point? And that single point is called the CG, is the center of the gravity. Or if the gravity doesn't change, you can also say this is going to be the center of the mass. And it turns out that location is the location where this point, then you have a smaller object on the left, you have a smaller object on the right. But if you calculate the summation moment with respect to this point, and it turns out to be 0. So this point is the point where you don't have any of the net moment. And if and this would be like simple idea as well. Like if you have, let's just make it simple. So this is going to be like just a bar. And it's a kind of a uniform bar. If we make a supporting point right in the middle, then this one will not rotate because of the weight of the bar, because the weight on the right and weight on the left is going to be the same and it's a uniform. So when you represent the weight on the right and weight on the left, they all try to make this term. However, their moment is going to be opposite direction, then their moment equal to 0. So with respect to this point, and this point actually is the center of the gravity. Okay, similarly, this is an arbitrary shape. If this is the shape of the bar instead of just like a rectangular bar, the center of the mass is not going to be at the center. You would expect the center of the mass is more toward to the base of this triangle, so it'll be more to here. As a matter of fact, this is going to be like a 1/3 of the length of the L if the total width of this one is L. Okay, so this is the topic you're going to study in this chapter here. Now let's look at how we actually calculate that. If we take the previous pictures, for example, so this is a body, and each one of the small object, they all have like dw and dw, right? The dw could be different as well. It doesn't have to be the same. And I wanted to find the centroid of this shape. Let's just make it as a two-dimensional so you can see how we do this, how we explain this. So this is a two-dimension, and this is the origin. And here is the center of the mass, or the center of the gravity, and this is going to be the total weight. We can pick any of the point. Let's just pick the point here, which is the origin. And then the moment due to this body can be equal to the total weight times this distance, which we're going to represent as the x bar here. This represents the center of the weight or the center of the mass. Starting from now, the center of the mass and center of the weight is going to be the same because we are looking at the gravitational is not going to change a lot. Okay, so if we look at the moment of this one, then the moment, the total moment is x bar times w. Total weight times the distance, and that's going to be the moment with respect to this one here. What about each one of this little dot here? If I look at the first star here, I'm going to find this distance. Let's say this is a W1 and I have a X1. If I look at this one, it's a W2 and this will be X2, so this will be W2. So I have like a X1 W1, this should be DW1, and plus X2 DW2. Now I have hundred and thousand of them. Each one of them is going to have a xn, dwn if I have m of them. Um, if you sum them together, or you make this one very, very small, it actually turns out to be like an integration. So it's going to be the integration like this. So this is going to be the same if you do an integration by looking at each one of the little trig here simply represent each one of this little piece of the body. It has a location away from the reference point, and then you multiply with the dw and the w. If we make this one like a uniform smaller particle, then each one of them just have the same amount of the dw. And this will be equal if these two equal, because they are simply just same object. We wanted to find a location where I can use the total weight to represent that. So it turns out from this equation, we put W on the right hand side, which is this one here. The total weight is equal to the integration of each one of the small weight. Is actually the sum of the total weight. So this equation is the equation that how do you find out the center of the mass. Similarly, you can look at the y, you can look at the z. When you look at the y, you look at the distance in the y direction. So if we look at this example here, the y will be this one here. So this will be like the y1, and this will be the y2, and this will be the location of our y bar. And three dimension, we just add another dimension. So this is the basic idea what you're doing now. You can replace the W to be the mass, right? So that's simply just everything will divide by the G. Or the weight is equal to the mass times G. So there's a mass times G, there's mass times G. G are the same, so it's going to be dm and dm, same thing. If you want to find the coordinate of the centroid, and then we talk about this, then you have to look at the shape. You don't really care about, you kind of assume this shape is uniform. The mass is not going to be depends on the location. Then the centroid is going to be the center of the mass, is going to be the center of the weight. We can use not only just the body, we can also look at the volume, we can also look at the area, we can look at the length. So we will show you how we do these kind of calculation in the later part. All right, so let's think about the centroid a little bit. The concept of the centroid is the geometric center of the object. We don't care about the mass. We think all the mass is uniform. Okay, or another word is homogeneous. So there's no change of the density. Therefore there's no change of the mass. There's no change of the weight. If this one is a symmetry, then it's very easy, because if it's symmetry, and then the centroid is going to be just right in the middle. But if it's not, then you have to do some calculation in order to find that. Now, book did give you kind of a table to show you. Let's just look at a rectangle. This is so simple, right? So if the base is the B and the height is the H, and the centroid is going to be one half of the B in the X direction, one half of the H in the Y direction. And if you look at triangle, triangle probably is another popular one. The you have to do some kind of calculation. So how do you do the calculation? Because this is a two-dimension. When you do a two-dimension for the centroid, we don't do the total weight, we do the total area if it's two-dimension. If it's the three-dimension, like this one here, you do a total volume. So the centroid, let's say this is the centroid location, then you do like the area and the top of this one is going to be the summation of the x for each one of the area. Okay, so this is how you do the centroid. Now we just want to start to give you an idea, but then later on we're going to do some calculation. All right, so here when you start to do the homework, you're going to have some problem that asks you to find the centroid of an area. And we just wanted to give you the step. So the first step is that when you see an arbitrary shape, you have to first to find a differential element of the area. It's kind of critical because if you don't see how we separate the object into smaller area, you might not be able to do the calculation, and which really most of them will require you to use the integration. So because when we want to find that, remember that this equation, this dA, you have to identify, oh, where is the dA? Okay, so you have to know how you define the dA at the very beginning. Over here, it gives you an example and give you some hint. So if y is expressed in terms of x, such as this equation, and you will use a vertical rectangular element. So what does that mean? If I draw the picture of this shape, so this is the x and this is the y. And if we represent this y equal to x squared plus 1, if x is equal to 1, y equal to 2, right? So if x is equal to 1, y equal to 2. If x is equal to 2, then y equal to 5. This is the x equal to 2, y equal to 5 here. Okay, so s equal to 3, then y equal to 10. Wow, so y equal to 10 and here, x equal to 3. So very likely the shape of this line is going to be like this. Okay, if the shape that we wanted to define the centroid is this shape. Okay, so this is the shape. And one of the side is going this way. And you wanted to find the centroid location and you want to find a dA, right? And this dA, it depends on how you define the area. So if we define the area in a vertical rectangular element, which means for each one of the smaller x, we are going to have a little rectangular like this. And this is what we define as the dA. And if this is the dA, so how do we represent this dA? How do we find out the area of this smaller region? Well, just assume this is a rectangular. If this is a rectangular, at the bottom over here, I can say this is just a dx. This is just a small amount of the x. But what is the y? The y is going to be determined by this equation right here. So this y is actually the x squared plus 1, and you multiply with a dx, and you do the integration, and that is how you find that part. Okay, so that actually is the second step. You're going to express dA in terms of the differentiating element of the dx, and which we are doing that. The dA is equal to x squared plus 1 times the dx. And then you have to determine the coordinate of the centroid. Okay, so if you do this way, if you go this way, you integrate with respect to different x, you are actually trying to find the location of the x. So you're trying to find a centroid location at the x direction, and this will be the total area. And on the top of that is going to be the integration of the x squared plus 1 dx. Okay, so that is how you find the centroid for an area. The similar step can be used if you want to find the center of the mass or center of the gravity. All right, so let's look at if we have an area and then we want to find a centroid, and what is the equation and how do we do it? In the picture that you see that we have an arbitrary shape, and the y can be represented as the function of x. Now it can be any kind of function. It could be x squared plus 5. It could be a more complicated equation like x plus 5x squared minus 6. Any kind of equation is possible. If you want to find the centroid location in the x direction, that equation is showing at the bottom blue color box. So the x bar, the bar 1 represents the centroid location in the x direction, and there's a y1 as well. And that is equal to some integration I'll explain a little bit later. At the bottom is simply just the total area. So arbitrary shape, but then you have to find a total area by doing the integration. You can do an integration with respect to the x direction or y direction, doesn't matter. But that's the equation you can use. If it's like a triangle that you probably know how to do the triangle total area, then you can just use formula to find the total area directly. Now the question is, so what the top part means. So top part means it depends on really where you look at that. So if we look at the first one here, we're looking at we try to find this one here. We try to find the x bar. So this is for this part here. We want to find where the centroid at the x direction. And we choose this vertical shape as the small area, then we do the integration. So this is our dA. And we need to use the center of this small area location to represent this area and multiply with the dA. So this small x with like a tilt on top of that, it's actually represent how far from the middle of this area to the origin of the axis that you're looking at. So that is this much amount, which is actually just a small x. But if you look at the y here, so let's say if we look at this area here, And we know the difference of these two height is just dy. And I still wanted to know how we do the integration of this part here. And this dA is still going to be the same. You're going to use this much amount, which is x, multiplied with the dy, right? So the dA over here is just simply x times dy. But what about this one here? This one is going to be with respect to the x-axis. So from this point to the x-axis, it's going to be this much amount. So that is the y that you put in here. Let's use a real example to show you the complete process. So now we have an arbitrary shape like this. The y is a function of x, and this is the function, which is equal to x cubed. The expand of this area is from 0 to 1 meter in the xy and also in the y-axis. And we wanted to use the same equation to find the centroid location. So the x bar is equal to the total area. And on the top, we have an x tilt dA, right? And we use this smaller area to represent the dA. And what does this one means? This means from the center of this small area, and we look at what is the x distance. So this x distance, this is the x distance, right? This is what this one is. And that distance is going to be the x that we put in here. If you use the same area and you look at what is the y tail means, so if this is the y, sorry, this should be a y bar. Right, if you use this one, and what does the y tail represent? The y tail is going to be from the middle of this area to the bottom of the x-axis, which is equal to y over 2. So a lot of people will make mistake to simply use y, and this is a different if you look at the y direction, that the x is still going to be, well, you can say, well, yeah, it should be in the middle of this dx, right? But the dx is so small, so it's approximately just equal to x. So this is supposed to be equal to this x plus dx, but because this one is very, very small, we just say x tail is equal to x. But for the y tail, it's the same. You're going to have this much of a y divided by 2. So it's the total height of this one, and we divide by 2. So we have x tail equal to x, but the y tail is equal to half of the y, or you can say half of the x cubed, because y is equal to x cubed. So using the idea that we can calculate what is the centroid of that one, we show you that x tail is equal to the x itself. dA is going to be the y dx, right? So the dA is equal to y dx. And what is y? Y is x cubed dx. So that is what this area is equal to. And it's from 0 to 1. So you do the integration of these two. The top is going to be different from the bottom. So the answer is 0.8. And if you want to find a y centroid, so the y centroid is going to be the y tilde dA over the dA, right? The dA is still going to be the same. And on the top of here, now this one become the y over 2. right? And what is y? Y is x cubed. So this one is the x cubed divided by 2, which is this one right here. And area is still going to be the same. And you do integration, and you got the answer, which is 0.2857. So this is kind of a key things that you need to do for this chapter. We're going to talk about the next one in the next video.